Hey, we're back with another related rate example. So in this example, I did not hide the numbers for you initially because we already talked about how we're not going to touch them until the end. And hopefully you've already written down this kind of 4-step process. So we're going to follow that every time. Again, we are never, ever, ever going to start a situation without drawing a sketch. The sketch is going to be what helps us pull all the information together and choose our equation. Because we're not going to be given one. You're going to have to find one, figure out which one works for the situation. All right, so this problem is, well, let's just read it. I don't want to give too much away. All right. A hot air balloon rising straight up is tracked by a rangefinder 500 feet from the liftoff point. Okay, so to spare you my drawing, I want a little clip arty. Okay, so I've got a hot air balloon and it's rising straight up, right? That's important because that way I know I have a 90-degree angle here. Okay, and it says it's tracked by a rangefinder. Now, I don't exactly know what a rangefinder looks like, but the idea is that it sends some sort of light or sound signal that bounces back and times how long it takes it to get back and then tells you therefore how far away it is, right? It does some calculation here, right? It sends a signal that bounces and then it does a calculation to tell you this distance. Okay, and it says that that is 500 feet from the liftoff point. So notice that I have this arrow going up because my balloon is moving. My rangefinder is not moving. They tell me it's 500 feet from the liftoff point. So I can come in here and I know that this distance is 500 feet. Okay, so at the moment the rangefinder's elevation angle is pi over 4. So they gave us this distance of 500. I'm going to call this x, right? I'm going to give that a name. I'll call it x. They're saying at the moment the rangefinder's elevation angle, so now I'm getting a new variable here. So the elevation angle would be the angle between the ground and this beam. Oops. Okay, so let's call that theta. Right. So at the moment that theta is pi over 4, the angle is increasing at a rate of 0.14 radians per minute. Now, again, related rate problems. Radians per minute. There's a big fat hint that you have a rate because it's a rate unit per, right? Radians per minute. Also, notice here, they used the word rate. But also they said it is increasing, which means when I write my rate down, I know it's going to be positive. Right? They said the angle is increasing. So what they just gave you there is a d theta dt of 0.14. Now, I am pretty diligent about this. I always write a positive 0.14 just because I want to get in the habit, and I want you to get in the habit of when you write down a rate, just always, 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 is it positive or negative? Every time, so that you don't forget. If you just get in the habit of writing it down, the absolute value of it, and then later worrying about it, it's easy to forget. Okay, so we know we have a triangle situation here. They gave us this x distance. They gave us a theta. They gave us a d theta dt. Since I know this 500 isn't changing, I can also write down that dx dt must be 0. And then there's this, which we haven't touched yet. Right? Last sentence says, how fast is the balloon rising? In other words, I need to define this height, right? I'm going to call it y just for fun. Because the question is, how fast is that height changing? So in other words, this rate at which that's changing is the big question. Okay, so big messy sketch here, but I've got 3 things kicking around. Long story short, I have a triangle at some point. Wow. This is y. I don't know what it is. This is 500, and this angle is pi over 4 at some point. Right. So I need an equation that relates all of the variables they gave me. Right? So minimally, They gave me a theta and a d theta dt. I need an equation that has a theta in it. And I'm needing to know what dy dt is, so I need an equation with a y in it. If x gets involved, so be it. But I absolutely need a theta and a y because I've got a d theta dt involved and I've got a dy dt involved. So our job is to find an equation that links theta and y. Okay. And again, let's go back to the idea that they said that that balloon was rising straight up. In other words, this is a right angle. So you can use right angle trig. Anytime you see a right triangle in your picture, there's two main things that you're going to have at your disposal as far as equations go. The first is the Pythagorean theorem, so like we used in the ladder problem. The second, anytime an angle is involved, the best, usually, course of action would be to go to your right angle trig, right? I need to find an equation that links this angle to this side of the triangle. Okay, so SOHCAHTOA, so SOHCAHTOA, right? This angle, this is my opposite side, this is my adjacent side. So I can easily use the tangent to link the theta and the y. And like I said, if the x comes in, so be it. Well, it does, because it ends up being the adjacent side. So here's what I know. The tangent of that theta at any moment has to equal my y over my x. And my x is 500. Okay. Now, since we know for a fact x isn't changing, it is okay to put the 500 in there, right? But it's also safe to leave it in. I'm going to do it with it in there so that you can see what happens. It's just going to fall out. Because it's not changing, it ends up falling out, right? So let me move my mug here. Okay. All right, so if I rewrite this as x, if I rewrite that equation as x times the tangent of theta is equal to y. On this side, I just have a dy dt, right? So that's nice because that's what I'm solving for. On this side, I'm going to have a product rule. So it's going to be x times the derivative of tangent, which is secant squared theta, d theta dt, plus the tangent of theta times the derivative of x, which is 1 dx dt. And so this is what I'm talking about. This whole term, because dx dt is 0, this whole term goes to 0. So it takes care of it for you. Now, if you had just put the 500 here, you would still have ended up with 500 secant squared theta d theta dt. So it's a wash either way. What I'm saying is, if you replace a number that you shouldn't have replaced, you can be missing variables from your equation. So the safest thing to do, if you're not sure, is to not plug it in. As a rule, if the number isn't changing, it's okay to plug it in. If it's a constant in the situation, it's okay to plug it in. It'll simplify your derivative. If it's not a constant, if it's changing, you cannot take it out. So if you're not sure, leave it in, because in the end, when you do your dx dt or your dy dt or whatever it is, if that rate of change is 0, it's just going to cancel the sucker out anyways. It's not going to matter. Okay, so I have that dy dt is equal to x times the secant squared of theta d theta dt. I've got everything I need. They gave me x, it's 500. I need the secant squared of theta, which is pi over 4. And I need to multiply by that by d theta dt, which is positive 0.14. So let's clean up here a little bit, because I want to show you a little bit of simplification Not that anybody would ever simplify, I know. Okay, so I have dy dt equals 500, the secant squared of pi over 4, right? So that is 1 over the cosine of pi over 4 squared. And then this is a 0.14 or a 14 over 100. Okay. So right there, boom, boom, you can make that a 5. Okay. 5 times 14 is 70, right? Okay. So I have, look. So this is a 70. Now, cosine of pi over 4. Root 2 over 2. Okay, so I got root 2 over 2, but it's 1 over, so it's 2 over root 2, and it's squared. So look at this. That's 4 over 2, which is a 2, and all of that hot mess comes out to 140. And let's go find our units. X was in feet, so my length is feet, and it was per minute. So I have feet per minute. Now, I'm showing you that again, not because on an open-ended you would simplify that. On an open-ended you would leave it. Please leave it. 500 secant squared pi over 4 times 0.14. Done. Goodbye. Circle it. Oh, don't forget to put the feet per minute on it. Okay. But multiple choice, they could put the 140 there on a no calculator section and you should be able to get to that. And it doesn't seem like you should be able to get to that, but you can, right? This looks like no way I can simplify that without a calculator, but you can. Okay. So just keep an eye out for stuff like that. And remember your unit circle. All right. That is the second way that we see a triangle problem. So the first one we saw, it was a right triangle and it was all 3 sides. So we used the Pythagorean theorem to relate it. In this one, still a right triangle, but there was an angle involved, so we used right triangle trig. Okay, so those are 2 pretty popular things. We see lots of right triangles in related rates. The next problem I'm going to do in the next video is going to be a completely different animal. It doesn't have a triangle involved with it, but it is also a really popular type of related rate question. So I will see you in the next video.